The next speaker is K.P.S.S. Hembram, and he'll be talking about bond fluctuating lattice polymers.
Rojit and Professor Srikant for giving me an opportunity to speak about what I have been developing for the last recent years. So the title of my talk is Development and Modeling of Nanostructures. So I belong to this center, JNCASR. So the outline of my talk will be three parts: modeling of properties of nanostructures. This I have been generalizing the concepts and the results of the other people who do experiment all over the globes. Subsequently, getting some of the inputs, I have developed some of the formation of nanostructures, how they form from atoms to molecules and to the nanoclusters. I will be giving some formulations that I have developed. Then I will show you the nucleation of the structures. Some of the researchers all over the world, they claim that the nucleation takes place at the random place. But some of the postulates that I have claimed, and I will prove to some extent that it's not random, it is happening at the definite places. Let us see how I am proceeding. So these are some beautiful nanostructures people grow in different environment all over the world. This is some nanorods, silicon nanorods. This is zinc oxide nanorods. This is zinc oxide petals, and this is also zinc oxides. These are some of the beautiful pictures, and this is the reference from where I have taken. If you see in the Google, you'll find so many different type of beautiful nanostructures, and these two I have grown in my laboratory, and these are multiple carbon nanotubes grown at different two conditions. And I have done some experiment to validate my predictions and my sets of law, not only in carbon nanotubes but also in different materials. Those are observed by different researchers and myself. So let us see the modeling of properties of nanostructures. Once we get the nanostructures of material, irrespective of the material, let it be metal, semiconductor, insulator, people generally see the properties. So different researchers are given different formulations. So this J. Wang et al., they have generalized the properties. They have given these laws once like this. This is the properties related to intrinsic length. This is the property of the bulk. It is expanded in terms of 1 plus alpha into property of small scale divided by properties of bulk plus higher order terms. So let us see term by term how it is applied in different context. In terms of melting, this is given by this scale law, where the L intrinsic length is defined in terms of like this, who is in this, if we take like this, it explains the homogeneous melting and growth of the nanostructures that differs from diameter to diameter the nanoparticle size. And from nucleations, again this theory holds. Again it holds for nucleation and growth of different substrate, different nanoparticles grown on different substrates. The same formulation holds for evaluation of stress at the nanoscale, and same formulation holds for the determination of Young's modulus of the nanoscales. So if those equations can tell the generalized scaling law of the properties of nanostructures, I asked myself, can I set some rules where I can tell the laws of formation of nanostructures? Yes, it's very simple. The matter in the universe stays mainly in solid, liquid and gaseous form, in the plasma form. Let us particular be specific about the solids case. You can in our world we have 3 axes and 1 time axis. So the matter will be spread into 3 along the 3 axes. So I have generalized the distributions of matter in this in this manner, where this is the distribution function, as the symmetry. This symmetry in specific crystal case, we can tell as a crystallographic symmetry. There are many other symmetries are associated with this. Presently, I do not know all the symmetries, but in this context, I can tell in the solid state it can be crystallographic symmetry. And these are the sets of parameter all the experimentalists all over the world play around to make different type of nanoparticles, let it be temperature, concentration of the solution, substrate, and electric field, magnetic field, or all the parameters. And this is the dimensions of the nano dimensions of the particle. Let us expand these equations. So, if I can expand these equations, I get similar terms like this. This is I define for 1D. If I take like this, it is for 2D, and this is for 3D. Here S, T and U are this symmetry that I explained before. These are the sets of external perturbant, or these are the parameters that all the experimentals play. These are the L for length, A for area, V for volume. So, yes.
This I index.
Oh, I equal 1 to 3, summation.
If this is summed over, then it cannot appear there.
Yeah, that I generalize because all the cases happens, so it can be summation over. Otherwise, what you told is right. It's alpha beta. Yes. Thank you. So let's take one experiment. This I have picked one paper from Ceramic Internationals, and they have found different size of nanoparticles at different temperature. And the three things I want to note it down. These A, B, C, D, E, they grow the nanoparticles at different temperature where they have scaled it like this. So number one, if in this case the temperature is constant macroscopically, then why there is Gaussian distribution of particles? Number one. Number two, if there is 20 nanometers particles are of this count is around 40, then why there is distributions? So even at small range of 20 nanometer particle size, they are not exactly 20 nanometers. Some may be 20, some may be 21. Why? I am going to address that. So this is the one example I have taken. The third thing is the facets that I am showing in the next figures. So this is the one schematic picture I have taken from this website. You can see roughly homogeneous of 10 nanometer dimensions of particle, 10 to 12 nanometers. You can say broadly. But if you see at the higher magnifications, see these particles and see this particle, you can see there is facets developments. So my claim is that even if there are two nanoparticles are there up to 50 nanometer size dimensions, they are having different number of facets. And I'm going to say why there are different number of facets also happening. And this is my own experiment. This what I have done. I have taken some tungsten oxide nanoparticles. I have grown on silicon substrate. You can see even these are two same dimension of the particles there. The number of facets are almost different. So how I studied? Let me go systematically. So this is a thin film growth by sputtering technique. This is a thin film. I grew at room temperature. I heat it around 400 degrees centigrade. You can see small platelet-like things growing. If I heat it at 500 degrees centigrade, the small platelet-like things breaks into nanorods type. If I take another sets and heat it at 600 degrees, some particles you can see some are nanorods type, some are nanoparticles type. If I heat it 700 degrees centigrade, then mostly are nanoparticles and some are nanorods. At 800, there is no particle, hardly there is particle because some particles get evaporated. So if I model it, suppose this is the one big plate, it breaks into nanorods. That nanorods breaks into nanoparticles. So this is the schematical picture I got from the experiment. So I generally found that in my case, the plate breaks into nanorods, nanorods breaks into nanoparticles, so like this. In my case, Suppose I start from the thin films, it breaks into nanoparticles directly. Some of the cases thin films goes to as nanorods, and the nanorods to nanoparticles. So let us define a instability wheel where the matter can transform one form to another form, getting one external perturbation. That external perturbation in my case was heat, and people can do experiment in terms of pressure and other of the things. So these things from nanorods to nanoparticles, this has been done by Rayleigh long ago. It's explained by Rayleigh instability. This has been some experimental from IIC only. They have grown some copper nanowires and they have heated around 700 degrees centigrade. So the copper nanowire breaks into nanoparticles. This is another set of experiment, and I have taken from this website. This you can do very easily. You can take a syringe and take some water and push it. So first few ejection side of the syringe you will find it is streamline, then it will form into droplets. Why this happens? It is given by Rayleigh instability. My key point that I have taken from it is the nanorods breaks into nanoparticles. It satisfies the 1/3 of the wheel from nanorods to nanoparticles. And I have done an experiment where I have gone from thin film to the nanorod, from nanorod to nanoparticles. And some of the cases I directly get from thin film to the nanoparticle. So this transformation takes place from this to this, and some of the cases this to this. If this is true at present conditions, I think in some other conditions the reverse can also happen. So maybe that is not known yet to the world's community. Maybe somebody will do in the future. So for sake of completion, I made one instability wheel where the matter can transform one form to another and vice versa. Yeah, this is the picture I have been telling once more. And this second thing, that is in conservation law. What I have been explaining, let us take for case of nanoparticles. So if let us take term by term, this term and second term, U1, gamma 1 and V1. Let us take the nanoparticles are grown at the two similar sets of conditions. Then if they form on the same crystallographic symmetry, then U1 will be equal to U2. Then if you see the volume V1 and V2 will be same, then we can confirm that these two particles have formed in identical conditions. So they are the sets of parameters gamma 1 and gamma 2 will be same. If not, then even if the V1 and V2 will be same, if gamma 1 and gamma 2 are not same, then they may form that 20 nanometer size particles with different facets. One nanoparticle may be having 20 facets, the other nanoparticles may be having 26 facets. Why? That I am coming in my later part of the talk. So this is another set of example. One of my colleague in Indian Institute of Science, he has done the experiment. So this is the zinc oxide nanoparticles, and so here you can see the hexagon from the top, and here you can see the hexagon, and but from the side you can see some rectangle, then pyramidal sides. Why this has grown? And this I attributed to the sets of parameters that I had explained in which falls in gamma 1 and gamma 2 conditions. But let us see from one of the facet from the top. Is it really this face and this face are same? Maybe or may not be. If it is same, then they are formed from the similar sets of conditions from the both facets. And if not, they are from different sets of conditions. But let us see this facet and this facet, all the facets forms one nanoparticle. It means that the surface energy associated with this surface and this surface energy associated with this surface multiplied with the surface area, they form one conservation law. So generalizations of this, the area of each surface and the surface energy of each surface multiplied with some proportionality constant. That constant is yet to be understood. It has to be constant, because this area of one shape and the area of this and area of this are different. Obviously surface energy of this and this will be different. So now the thing has to find the proportionality constant from one surface to another surface. This has to be done and theoretically verified. Now I am approaching through density functional theory. I know how to calculate the surface energy of this surface and this surface. In future, maybe in the next, I will be able to come with the answers of epsilon 1 and epsilon 2, the relation between 1 to 2. So let's see, once the nanoparticles are formed, then all the properties we are able to know. But how they form? I made another sets of law, the law of formation of nanoparticles. This is the functional, this is mx plus c. If you see in mathematical, this forms a straight line. Let us see. I have taken one set of experiment from the literature. These sets of people, what they have done, they have grown one titanium thin film on the silicon substrate. They have done the electrolysis experiment, and if they change the anodic voltage, and they get different pores, and they have plotted the anodic voltage versus the interpore separation, and they form a straight line which is given by d equal to some constant plus 2.81 u, where the governing factor is UA, which the experimental is controlled. This is for 1D or nanopore. This is another set of experiment. They have grown some zinc oxide nanorods on the silicon substrate. They have done the experiment with a different concentration of acids, and they also form one straight line in this case and in this case and in this case. And this anomalous behavior they have explained interquarsoning, but mostly they define this also forms a straight line. The governing factor C is the concentration of the solutions. So in the previous case, it is the anodic voltage which plays the major role, and in the second case this concentration of the solution which plays the major role, and both the cases this forms a straight line. This is, and these are 1D case, means it is nanopore and nanorods case. Let us see the 3-dimensional case. In my case, I assume that nanoparticles are 3D. Again, I have taken the same paper, and they have formed the log D. The dimension of the nanoparticles, it forms 3.06 some factor divided by T, and it forms a straight line that I had shown you previously. But they have done at different temperature. This is the plot, and the governing factor is temperature. Here the governing factor stays are the denominator. If they plot log versus the dimension, it forms a straight line. So the key feature is that in case of nanorods and nano pores, the dimensions of the rod follow straight with the concentration or the anodic voltage. But in case of 3D, the governing factor stays the denominator if we take the logarithm case. So what happens to the 2-dimensional case, which is the thin film? I did the experiment. I grew some of the thin film. I did various like TiO2, ZiO2, tungsten oxides, all the thin films I grew. So I did mostly by thermal evaporations and sputtering, although there are CVD and MV growths are there. So the key factor in the sputtering or all the cases is the rate of depositions. Suppose this, let us T1 is the thickness of this particle. It depends upon dm by dt. Dm means the rate of depositions of the particles. So if we T total thickness, it will be integration of T. So I thought, let me scale this to equation in one simple form, where let me get one straight line, and the key factor, so I put empirically this formula so that it will form a straight line. So the rate of depositions I have put in this factor, so I should get a straight line. So generalizing this thing, for case of nanorods and nanopores, this FD is a straight line. For nanoparticles, log D is a straight line. For thin films, this is a divergence term which is related to rate of depositions. It forms a straight line. So this is the way I scaled all the three process like 1D, 2D and 3D, and I made a straight line. So this is the scaling law of formations. I hope this will validate all the physical process all over the world, irrespective of the deposition condition, irrespective of the preparation process. It will follow all the it will follow all the formation of nanostructures. So to summarize the development of nanostructure, this is the law for distribution of nanoparticles, this is the conservation laws, and this is the loss of formation of nanoparticles. And this instability wheel tells me if I give the external perturbations, the matter will transform from one environment to other environment. Let me give some glimpse about the nucleation of the structures. People have claimed the nucleation takes place randomly, or where it takes place nobody knows till now. But I claim, I have given two sets of postulates. I can roughly tell which place the nucleation takes place based on some of the simple observation from quantum mechanics, from wave theory. First, the nucleation sites. The nucleation doesn't place randomly to any of the processing conditions. It takes place at the constructive and destructive interference of the waves. Those are associated inside inside some environment where the matters are there. Let me give some examples. You have constructed the theory. Let us take the model example, particle in a box. Suppose this is a potential barrier or particle in a box. So suppose some waves is coming. So some waves get reflected, some waves get transmitted, and from here some waves gets also reflected, and some of the waves goes away. Think in associations, this is my experimental chamber, or this is my material where the nucleation is going to take place. So these are the sets of waves. These waves may be the electromagnetic waves, and it may be some others. In physical sense, it may be the temperature, pressure, electric field, magnetic field, any other things. So the waves which are there in between, they forms constructive interference and destructive interference. And in this condition, you can think these are the interface. In open condition, you may not have interface, but still you will have some constructive interference and destructive interference of the waves. Just like in double slit experiment, these are the interference patterns. And you will find some of the waves, these are where n equal to 4. So the places where the constructive interference takes place, I claim in one way, those are the place of nucleations. And the place where the destructive interference takes place, those are not favorable for the nucleations. Why? I am claiming the second postulates. The second postulates that people tell the density fluctuation happens in the before or in an urban environment. Why the density fluctuation takes place? Then to quick approximation, quick answer I can tell that the waves which are associated inside the matter drags somehow the matter. How they drag, even I do not know. But the thing that I can think, it drags the matter some way. So that's why people get the matters, the nucleation densities are higher in some of the cases and lower at other places. The places where it gets the critical densities, those are the places where the nucleation starts, and not all the places. These are my two postulates that I am claiming. Okay, the second example can be given by the Rayleigh instability. Suppose you take a wire and you give thermal heat, so it will form into nano dots. So some waves are associated with this drags matter from this region to this region. This is one of the experimental clue I have taken from the literature. Again, I have done on this experiment also. The summary of the nucleation of the structures, the postulates that I am claiming, the places of constructive and destructive interference of the waves The exact nature of the waves is still yet I have to investigate. Are suitable places for nucleations. It's not random. The waves drags the matter leading to density fluctuation, and these are the beautiful structures. The overall conclusion, the modeling of properties of nanostructure, this is given by literature, and these are the sets of things I have claimed, not exactly this, and the instability wheel. The nucleation of the structure, I have given two postulates like constructive and destructive interference of the waves are the suitable place for nucleations, and the waves drags the matter in some or the other way. Thank you very much. I thank to Maxwell and JNC because I belong to this place. I'll be happy to take some of the questions.
You see, I don't know how to actually put it very politely, right? The last part is not believable.
Yeah,
okay.
Because...
Well, can I finish, please?
Yes.
Yeah. So, when you make a hypothesis, when you make a conjecture hypothesis, I think you ought to have the responsibility to tell where that comes from. You can't say that the waves are there and I do not know where they are coming from. That's not a responsible practice, I think. But leaving that aside, let me ask a technical question, right? So let's take zinc oxide nano crystals, right?
Yeah.
So you have needles and you have discs, right? Okay, now let's take needles which are normally formed, right, when you make a zinc oxide crystals, right? Mm-hmm. Now, suppose I sprinkle a little bit of polypeptides into the growth medium, which have some histidines, for example.
Yes.
We know that they make spontaneously, they convert, the needles transform into discs.
Yeah.
Okay, how does this go into your parameterization?
Yeah. Number one thing that you asked about those waves. The thing that I am concerned, or all of you are concerned, is here. The waves which you are giving or which are taking away from the systems are something like the temperature. If you reduce the temperature, or if we give the temperature to the heat, to the systems, so the particles or the atoms, let it is in a solid form, so the atoms will vibrate and they will generate different kind of waves than the incident waves. Those kind of waves I am speaking about. Those kind of sets of waves, because in the interface so many atoms will be there. Those waves generated from so many atoms will make interference among themselves. Those kinds of waves I am telling. Second question. You told that in some of the conditions people get nano needles. My experience tells that in sputtering, in CVD, I don't get needles. On the other hand, if I grow the zinc oxide nanoparticles in thermal beam evaporation or E-beam evaporation, yes, I get. There the probability of nano needles are more. The question that you ask, if you give some,
Say put some polypeptides.
Some polypeptides, there I am explaining in terms of instability wheel. Suppose you have nano needles, give some polypeptide. So those are some external parameters. It will drive the system from nano needle form to thin films.
You talk about Raleigh's instability.
Yeah.
So what is the driving force for this, to have this instability?
Raleigh explained in terms of, suppose you give the external perturbation, that is the heat. The heat, the explanation that they are given in this external perturbation is the heat. And there are some mechanisms where the matter transforms from region to this region.
Okay. So in some of the slides you talk about the breaking up, transitions of shapes of W3 thin film into nanorods or particles.
Yeah. Those are the sorts of experiment I did.
Yeah.
Yes.
So what are the parameters that cause this transition?
Yeah. So I grew the thin films by sputtering techniques. I made so many samples, let it be 10 or 15. I took one of the samples, put in one chamber, evacuated in 10 to the minus 6 millibar. Then I heat it to 400 centigrade, one set of sample. heat it another set of sample 500 degrees centigrade, like that 600, 700, 800, 900. So these are the different temperatures I have post annealed the samples. This is one condition I got. In second set of experiment, I grew the samples. I did not break the vacuum. I hit the sample, let 700 degrees centigrade, I got this type of. So the only thing that I had given is the temperature, nothing else.
So you think time don't have any role to play here?
Time, yes, time also plays.
Atmosphere?
No, because there is no atmosphere. Because
You break the vacuum in one case.
in one case, in another case, I don't break the vacuum. I get the similar phenomena. Huh?
When there is no vacuum in that case,
Yes.
in that case, what is the effect of atmosphere surrounding ambient?
Okay. The first thing that my tungsten oxide will get attacked by two major dominant gas molecules. One is nitrogen, one is oxygen. So if I take those things and put inside the chamber, again evacuate it, I guess some of the adsorbent molecules which are there on the surface, it will go out. Because I got reproduced without breaking the vacuum also. Yeah. Yeah, just a minute, I'm coming.
Yeah, see no, this is not it.
Okay, because
you had that law of distribution.
yeah, this is the law of distributions.
Uh-huh. Yeah, okay.
Oh, this is the hash.
As far as I can tell, I mean, I can't make head or tail of what that means. What is that a distribution of?
Distributions.
And can, wait. Huh? So it looks like you're just throwing a bunch of symbols together. And if I asked you to make a calculation of anything, you can't use that formula. Is that correct? I mean, have you used that to do anything, do any calculation?
No, but I got from the experiments.
Some numbers on the right hand side and get a number on the left hand side using that formula and interpret what that number means?
This means the symmetry, these are the sets of parameters. Suppose in simulation we can put something like temperature or pressure or some other things, and maybe somebody has done, so they have taken
have you done this exercise for any particular system once and interpreted the left hand side?
experimentally done, yes, theoretically no.
So can you tell us what went into the right hand side and what went into the left, what came out of the left hand side?
Left hand side is the distribution, how matters are distributed.
What?
And right hand side, so the matter will be distributed in like, so this is for 1D, this is for 2D, and this is for 3D. So this is the all nanorods or nanopores which are formed in these sets of conditions with this symmetry.
Okay, you're not answering my question. So
Going from carbon rod to nanoparticles by giving thermal energy, right? 500 Kelvin, and that thermal energy is basically your waves that is breaking your nanorod in nanoparticles.
Yes.
Now you are saying that you have an instability wheel where you can go reverse direction also you can go.
Yeah.
So in that sense, can we take out the temperature by lowering the temperature? Can we go from nanoparticles to nanotube?
No, in this case, that's what I told, that in this case, the reverse case, the experiments are very less. Maybe some other conditions, some suitable experiments are there. In this case, yes, it is no. That's why I told, if it is possible, in some other condition, it may possible.
So that is possible if we can retrace our waves back.
May not for with this experiment, maybe some other experiment.
So means in that experiment, that instability
Maybe,
wheel is possible if we retrace our waves back.
No.
Maybe we can discuss this over coffee.